Hi! So in today's video, me and my little rubber ducky are going to be teaching you how to balance three separate redox reactions using three separate methods. The methods we will be going through are 1. Oxidation numbers, 2. Ion electron method in acids, and 3. Ion electron method in base. Alright, so for the first example we will be going through, we will be balancing a chemical equation using oxidation numbers. In balancing the chemical equation using oxidation numbers, there is a total of 5 general steps. A few in-between steps, but these are the 5 main ones. So this is the chemical equation we will be balancing. So let's just get started with step number 1. Find your oxidation numbers. When looking for my oxidation numbers, I want to go through all the ones I know first. So those would typically be the ones you've memorized, like oxygen and hydrogen. All the other ones can then be solved using a small algebraic expression. So let's do just that. Go from left to right. In this case, I'm going to use a red pen, but N is not one of those atoms I've memorized the oxidation number. But I do know O, so O is almost always -2 oxidation number. Now moving on, hydrogen, in this case, it's a lone atom with no charge. Lone atoms with no charge are going to have an oxidation number 0. H2O, a water molecule, this is one that shows up a lot within a lot of these questions, so you should have it memorized, but in this case, you know the oxidation number for hydrogen and you know the oxidation number for oxygen as well. So we can just put those down. -2 for oxygen, +1 for hydrogen. Now we see a nitrogen again. We're going to skip that because we haven't memorized. Hydrogen is +1. So now we're going to go back to the nitrogens and solve them using a small algebraic expression. This is how it's going to work. We're going to write it out just like a math equation. N plus O equals the total charge of the actual molecule. In this case, this molecule doesn't have a charge, but let's say it did, like -1, then we would put -1 as the total charge, but it doesn't. So its total charge is going to be 0. Be careful because there's 2 n's here, right? So we're going to multiply the n by 2. Using this algebraic expression, we can substitute the O with its oxidation number because we already know its oxidation number. Then, the only variable we'll have left to solve for is going to be the nitrogen. Therefore, N's oxidation number is +1. Write that down. +1. We're going to do the exact same for this N on the product side. Let's write that down. Just like that, we've completed step 1. So, moving on, we need to identify our half reactions. Now, for this next step, the half reactions, there's going to be one reduction reaction and there's going to be one oxidation reaction. Remember, reduction means you're gaining electrons and oxidation means you're losing them. So, to find your two half reactions, we're basically looking at the oxidation numbers we've written down in the previous step, and we're going to see which atom had a change in charge or oxidation number as it went from products to reactants. So let's go from left and right and analyze each atom. Nitrogen had a +1 on the products, and as it went to the reactants, we see it changed to -3. So right away we know that nitrogen is going to be one of our half reactions. So we're going to use a blue pen to arrow the first nitrogen to the second nitrogen. And then we're going to find our second half reaction. In this case, oxygen. Oxygen had -2 here, had -2 on the other side as well, so that's not a half reaction. Hydrogen, however, had a 0, and it turned into a +1. But at this point, you might be wondering, there's also a hydrogen in the NH3. Well, technically, theoretically, we could use that one, but it would be a lot harder. Alright, what we're aiming for is we want to use the molecules that haven't already been used in a half reaction to make life easier, right? So we're going to use the hydrogen in the H2O. instead of the NH3. Boom. So what we're trying to basically find in these half reactions is how many electrons has each atom within the half reaction, one that we're analyzing, lost or gained. So in this case, let's do the nitrogen first. Here it had a +1, then it turned into a -3. Remember that electrons have a negative charge, so the more electrons you have, the more negative your number will become. So we had a +1, it goes to a -3. That means it got more negative, meaning we gained more electrons. How many did we gain? Well, that's just a bit of simple math. We gained a total 4 electrons here. So we're going to write on the line for the N, gained 4 electrons negative per, and this is a very important step, per 1 hydrogen atom. Now we're going to do the exact same for the hydrogens. We went from a 0 to a +1. That means we lost electron. Negative per hydrogen atom, right? The number got more positive, so clearly lost an electron. Now we have to identify which one is our reduction reaction and which one is our oxidation reaction. Remember, oxidation means you've lost electrons in the process. Reduction means you've gained them. So this one we gained, so therefore it's going to be a reduction reaction. We'll identify that by writing a little R, and this one we lost, so we're going to put a little O. Alright, so that's done with step number 2. Moving on to step number 3, halfway there, subscripts. So basically with subscripts, all we have to do is identify if there is a subscript within the half reaction we're analyzing, the atom specific analyzing. So in this case, let's start with the nitrogen of the reduction reaction. See, there's a subscript of 2. On the right side, there is no subscript, but all we really need is one subscript. The subscript will help us identify what our coefficient will be in front of the molecule later on. So we're going to take a yellow highlighter and highlight that subscript that we see there. Now we're going to have to put it in the actual equation here. So we're going to, because we have a subscript of 2, we're going to multiply it by 2. And the reason why we're doing that is because here it says we gained 4 electrons per 1 nitrogen atom. In this case, we have 2. So we multiply by 2. Now we have a total of 8 electrons here. We're going to highlight the multiplier in the reaction as well, the 2 there as well. Now we're going to do the exact same thing for the other half reaction. The hydrogen has a subscript of 2. Here it also has a subscript of 2. Just going to highlight both of them. Now we put it inside of the equation we have going on down here. So times by 2, 2, negative, highlight the 2, and there you go. We're done with subscripts. Moving on to step number 4, lowest common multiple. Now the lowest common multiple refers to the lowest common multiple between the total number of electrons we've calculated between both half reactions. So in this case, the oxidation half reaction has a total of 2, reduction one has a total of 8. Lowest common multiple between 2 and 8, of course, is 8. 4 times 1. We're going to write that down in this little equation we have here. So 2 times 4 gives us 8 electrons. And this one we don't have to multiply, it stays at 8. We're going to make sure to grab another highlighter and highlight that multiplier. So in this case it was 4 hydrogens. Nitrogens didn't have one for the reduction reaction. Now we're at the step where we can finally find our coefficient in front of the molecules. So looking at our nitrogen or the reduction reaction, our highlighted numbers are going to suggest what our coefficient is going to be. In this case, we have a highlighted number of 2. This comes from the subscript, but in this case, we can't just go ahead and put it as a coefficient because we see that it was already accounted for, the actual molecule, as a subscript of 2. So we don't need to, or we're not going to put it as a coefficient. looking at the right side, this is the opposite actually. It was not accounted for. So we are going to put that as a coefficient in front of this molecule. 2. So there we go, we did the reduction reaction. Moving on to the oxidation one, we have 2 highlighted numbers. In this case, these numbers can combine to give us essentially a coefficient of 8. However, if we look at the 2 atoms we're analyzing here, 2 has already been accounted for in both situations. So we're not even going to combine it. We don't need the 2 in either atom, but we will be using the 4. However, before we just aimlessly put the 4 as a coefficient in front of both, we need to use a little bit of logic here and some grade 11 balancing to identify that we can't just do that because it won't end up balancing out at the end. The 4 will definitely go in front of either one of these molecules, but it's not always both. In this case, I'm going to put the 4 in front of the H2 because if we look at the right side, two H's, and then we have 2 times 3, which is 6. So in total, we have a total of 8 H's on the right side, and here 4 times 2 is 8. So the H's balance out. We won't even have to put the 4 in front of the H2O here. Moving on to our final step, grade 11 balancing. Well, if you look carefully, boom, potato, tomato, all of this is already finished. It's balanced. We don't need to do any grade 11 balancing. The oxidation numbers, the process of lowest common multiple and subscripts have already balanced it out for us. Nitrogens, 2 nitrogens here, 2 here. Perfect. Just like that, you've balanced your first equation using, or reaction using oxidation. Now we're going to move on to balancing a reaction using the ion-electron method within an acid. Now there's a total of 4 steps for this one, 4 general steps, and this is the equation that we will be balancing. Let's start with step number 1, find your half reactions and balance. Now in finding your half reactions is pretty simple. All you're basically looking for is the same atoms that were in the products that are now, or that were in the reactants that are now in the products. So in this case, we have zinc in the reactants and zinc in the products here. That's going to be one of our half reactions, reaction number 8. And then our second reaction is going to be the NO3 and the NH4+. Now, you have to balance anything that is not a oxygen or a hydrogen. So in this case, everything is already balanced for us. We have additional balancing we have to do, other than the oxygens and hydrogen. Moving on to step number 2, use your chart for the OH and electron balancing. Now the chart is what we're going to draw out right now. Basically, this chart summarizes what we're going to add to each half reaction in order to balance our oxygens, our hydrogen, electrons. So for every oxygen, we'll be adding H2O, water molecule. For every hydrogen, we'll be adding H+. And this is specifically for acidic. Then for electrons, we're just going to say that electrons. Eventually, we're going to balance out the charges. That's what the electron. So we're going to use this chart in order, starting from the oxygens, working down to balance both half reactions. So starting with half reaction number, or letter A, we have zinc and zinc. In this case, we don't have either a oxygen or a hydrogen, so we can skip right to balancing the number of electrons. So if we look at the charges on both sides, this one has a total charge of 0, this one has a total charge of 2. We can clearly see that we need to add 2 electrons here, because electrons have a negative charge, in order to balance this half reaction out. Now again, looking at our oxygens first, we see that the left side has 3 oxygens and the right side has 0. So in order to balance that out, we're going to add 3 H2Os to make it even. And you can see how that balances, because if we have 3 O's on the left side, by adding 3 H2Os, we also add 3 O's on the right side. However, be careful, because by adding the 3 H2Os, you're also adding 6 hydrogens, along with the other 4 on this side, which we will balance out right now. The H. For every H, we add a H plus. This side has 0 H's. This side has a total of 3 times 2, 6. 6 plus 4, 10. So we need to add a total of 10 H pluses to balance it up. Now we move on to the final step here, which is balancing out our electrons. On the left side, we have a total of 10 minus 1, 9 electrons. And on the right side, we have a total of 1. We have a 9 charge here and a 1 here. That means now we need to move on to the final step, the chart method, which is balancing out our electrons. So on the left side here, we have a total of 9 charge. Positive 10 minus 1 is 9. Then on the right side, we have a total of plus 1. Plus 9 plus 1. So we need to add 8 electrons to the left side in order to the right side. So we'll add plus 8. And this is always a good thing to keep in mind. If you're doing all of this correctly, the electrons on the electrons on both half reactions should be on opposite sides, just like they are here. Now we can move on to step 3, which is finding our LCM for our electron charges. In this case, in our reaction A, half reaction A, we had a 2 electron charge added, and in reaction B we had an 8. The lowest common multiple between 2 and 8 is 8. To match that, multiply this whole reaction here by a factor of 4. By doing this, we will match the electrons. We'll have 8 in both half reactions. However, by multiplying it by 4, we need to multiply all the other atoms as well by 4. Lastly, before we get into the next step, it's important to identify which one is our oxidation and reduction reaction. So our A half reaction is going to be our oxidation one. We are losing electron reaction, and then our B one is going to be our reduction reaction, gaining electron. So at this point, we've reached our step number 4, which is rewrite our equations after we multiplied everything and cancel out like terms. So as you can see here, all I've done is I've rewrote both reaction A and B, but remember we have to multiply the zincs by 4 along with the electrons. The electrons I've already done. 2 times 4 is 8, but the zincs we also have to multiply by 4, so it'd be 4 zinc here, 4 zinc there as well. Reaction number B stays the exact same because we did not have to change the lowest common multiple for the electrons in that reaction. Now we can cancel out like terms. The electrons, if you've done this right, should always cancel out because you found the lowest common multiple for them. And if you have any other things that cancel out, you should do that, but in this case we do not have anything, so we can just go straight into our therefore statement and rewrite our equation as one whole, combining both reactions. So at this point, for my therefore statement and final answer, all I've really done is just combined everything that was on my reactant side, everything that was on my product side from both reactions, and put it all into one. This is my final answer. Alright, so for our final question, we will be balancing using the ion-electron method in a base. And if you've been pretty observant, you'd probably see that the steps are the exact same. So the only thing that changes here is the chart. And although it may look a little bit more hairy on the surface, just like my arm, do not worry, I actually think that balancing in a base is easier than in an acid. Alright, so this is the reaction that we will be analyzing. And I already went ahead and wrote out your two half reactions and the chart we will be using for a base. As you can see, it does look a little bit more different than the chart we used for an acid, but don't worry, it actually works itself out most of the time when it comes to balancing hydrogens and oxygens, unlike the acid chart. You'll see what I mean in just a second. So step number one is draw your half reactions, which we've done, and balance anything that is not a O or a H. And this is actually the first time we see where a atom that is not an O or H is not balanced. So in this case, our Cl, we have 2 on the left side, we have 1 on the right. So in order to balance that, I'm just going to put a coefficient of 2 on the right. Now, look at the bottom one, Cl, there's 2 on the left, 1 on the right. Again, put a 2 on the right side and it balances out. Now we're done that step, we can move on to step number 2. Use chart to balance out the O's, the H's, and the electrons. Now, in this case, we're gonna work our way down the same way we did for the acids, so starting with oxygens, and then hydrogens, and then electrons last. But you see there's different molecules being used here, and there's actually a slash. What the slash represents is that for every 2OH negative we add to the oxygen deficient side, we will add a H2O on the other side. So let's go ahead and try it out. The same rule applies for the hydrogen. For every H2O we add to the hydrogen deficient side, we add a OH to the other side. So let's try it with reaction A. In this case, we see reaction A starting with O's. We have a total of 6 O's. Remember the coefficient. 2 times 3 equals 6 O's. So to match that, we have to add 6 2OH's, but remember there's a coefficient in front of the OH negative. So we're going to multiply 6 times 2, 12. We're going to add a total 12 OH negatives to the left side, but for every 2 OH negative we add to the left, we have to add H2O on the right. So we added 6 2OH's on the left, we're going to add 6 H2O's on the right. Next, we can move on to the hydrogens. Now, unlike the acid, the O's and the hydrogens that come along with the molecules we use for O's balance themselves out. As you can see, we added 12 H's from the OH, and by doing that, we also added 12 H's on the right side from the H2O's. So we don't have to balance anything out. There's no additional H's within the original half reaction. So we can jump straight to the balancing of electrons. So when it comes to balancing the electrons, on the left side we have a total charge of negative 12 negative OH's. And then on the right side we have a total charge of negative 2. So we need to add a total of 10 electrons to the right side in order to make it equal to the left side. 10 plus 2 equals 12. So grab the red pen, plus 10 electrons negative right side. Now we can move on to the second half reaction, and the second half reaction is actually a lot easier because you'll notice there's no O's, there's no H's. All we have to do is just balance out the electrons. So on the left side there's 0 charge, on the right side there's a negative 1 charge. So we have to add, oh, but be careful, I almost messed up. So there's actually a coefficient of 2, so there's actually a negative 2 charge on the right side. We need to add a total of plus 2 electrons negative to the left side, balance out those electrons. Now we move on to our next step, which is LCM of electrons. In this case, we had 10 electrons on the A reaction and 2 electrons on the B reaction. So LCM between 10 and 2, of course, is 10. Multiply this whole half reaction by a factor of 5 to match those 10 electrons. But remember, by multiplying by 5, we multiply everything by 5, including the CLs here. Again, lastly, right before we move on, let's identify which one is our oxidation reaction and which one is our reduction reaction. So in the reaction B, we went from Cl minus, so we gained an electron. In that case, that is going to be our reduction, making the A reaction our oxidation reaction by default. Now, once again, I went ahead and rewrote the two half reactions. However, remember we need to multiply that 5 by everything within the second half reaction here. So I already did it for the electrons. We got 10 electrons, they're matching. Now I just need to do it for the CLs. So 5Cl2, and in this one we had a coefficient of 2 to begin with. It'll be 2 times 5, 10Cl minus. We are now on our fourth step, where we have to rewrite the final equation and cancel any like terms. In this case, remember the electrons should always cancel out if you've done everything right, and we can rewrite our final equation because there are no other like terms that can cancel out. One additional thing I will mention, this is my final therefore statement, and you'll notice that I've technically gotten rid of one Cl. Well, I didn't get rid of it, all I did was just combine it with the other Cl in the reactant side of the second half reaction. So we had 5 Cls in half reaction B and 1 Cl in half reaction A, Cl2s, and I just combined them to get 6 Cl2s. Lastly, in a question like this, you'll notice that the coefficients in front of all the molecules can all be reduced by a factor of 2, so your final statement should be a reduced version. And there you go. This would be your final fully reduced balanced equation from using a base. Alright, I hope the video was helpful. Otherwise, I'll see you next one. Peace.